begin by doing a quick little recap of what we've done already with logarithms and defining what a logarithm is. So I just want to make sure that it is clear the difference between or the connection between roots and exponential or the multiplication table and roots and the exponential functions and logarithms and the inverse properties between them. How should we do this? How about let's see if this helps. So let's say we have a table, we have x, and then we have x to the power of 2. So let's do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and good enough. Okay, so this is going to be this one to the power of 2, and then that one gets all squared. All right, good enough. Okay, so here are tables including all our powers, right? So I put power here because I knew that the Excel program was going to put x, it's going to do this. If I had done it, I would have done that, and I know we're not used to doing that. So we could still write this down as like function notation. If this is the input x, then, I don't know why that's so thick, okay, then this would just be x squared. We can also write it down as f of x equals to x squared, right? So we're squaring all our powers, 0 squared, 1 squared, 2 squared, right? The input is this guy, and the result is that we squared, and here's our table. Raising to the power of 3, here's our input x, and so here is some other function, I don't know, I can use g of x equals to the input raised to the power of 3, right? The input gets cubed, and here's our little table, right? 4 times 4 times 4 is 64, and 5 times 5 times 5 is 125, right? That's what these values are. Let's just confirm some of these things. So this one right here is 3 times 3 times 3. That's what 27 is, right? And this one is 6 times 6 times 6, right? Okay. Then we have this other case over here. This is an x, and then this one is some other function. Let's call it h of x equal to x to the power of 5. Right, so 0 times 0 times 0 times 0, 5 different times. That's how we get this. 1 to the 5th power, that's still 1. 2 to the 5th power, that's 32. 3 to the 5th power, that's 243, right? So this guy right here, for instance, is 3 times 3 times 3 times 3 times 3. 1, 2, 3, 4, 5 different times. That's how we get this 243. And then self-explanatory for these, right? So let's just write down a function for it. I don't know, about w of x equals x to the 10th power. I don't know, about v of x. V of x equals x to the 8th power. Good. Okay, so we have all our tables, and we learn these, and then we want to learn how to go backwards, right? To go backwards on these tables where you have an input raised to a constant power, that's when we invented roots, right? So roots, so if we go root 3, right, the index of the root is this little 3 here, it means to go to this table, right? As soon as you see this index, this notation, this symbol, it means go to this table and read it in reverse, right? You're going to go to this table and read it backwards. That's all you're doing. There's really no magical new power you learn from this. It's just learn how to use the table and go backwards, or have it memorized, right? So if we see the cube root of 729, you either have this whole table memorized, or you're brilliant, or you have a calculator, or you have a table. And you go to the table and you see, okay, well, it's cube 3, root 3, so we got to go to this one, and then we got to read it in reverse, and so that's how I know that my answer is 9. Good. Or if we see another table, and okay, this one says root 10 of, wait a minute. Oh yeah, the 10th root of 59,049. Okay, so I know that I have to go to this table over here, something raised to the power of 10, and then I have to look for this number if I can find it on my table. And that's how I know that the answer is 3. Right? There's no magical property to this root notation. You just have to know to look at the table. Now this works for the whole number values. Of course, what about decimal values? Okay, well, we have to extrapolate from that a slightly different idea, or thinking about the graphs and thinking about approximations. But in terms of whole number solutions, this little notation here should not be that special, right? We should at least get a concept of what this means, right? We have to go to this table, we have to read it in reverse. That's what this means. Good? Okay, so raising an input to a constant exponent is related to roots, right? Okay, so we're going to do the same thing with exponential powers, but we want to go backwards on those. So let's do that with this thing again. So I'm going to change this to say base 2. Okay, well, that was a long investment. Hopefully it pays off for anybody that's still a little bit confused. Okay, so then we have new functions. Now we have a slightly different situation. In the previous one we had x squared, and here we have exponential functions. So this one, for example, could be written as 2 to the power of x. So this one could be f of x equals to 2 to the power of x. So as a result, say this one, this 8 right here, is the result of 2 to the power of 3, which equals to 2 times 2 times 2, which is how we get that. And say this one over here is 2 to the power of negative 3, which is the same thing as 1 over 2 to the power of positive 3, which is the same thing as 1 over 2 times 2 times 2 equals 1 over 8. 1/8 gives you 0.125. Good. Okay, so then these ones, let's scoot this down a little. So let's move on to these. So if I define this as some function h of x equals to 3 to the x power, we get this one, and define in a similar way. This could be some g of x function, which is 5 to the x power, some w of x function, defined as 8 to the x power, and finally some v of x function, defined as 10 to the x power. Okay, so we know how to move forward with these functions. We know that the input is now in the exponent. That's different from before, right? That's similar to the previous one where we had x to the second power. Don't confuse these two, right? The input is the base being squared for the previous functions, whereas here we have the whole number, the constant value of 2 is the base, and the input value is the exponent. Okay, so they're a little bit different. And now if we want to go backwards, with these, to go backwards, the reverse was, the inverse of this was roots. Inverse. Oh man, this is not helping. I don't know why sometimes my computer is doing great and sometimes it just really does not like life. Okay, the inverse is roots. Okay, well, in this case, the inverse, to go backwards, to read this table in reverse, we're going to use the notation of logs, right? That's where logs were created. So when you see the word log, there will be a little index here, just like in roots. So let's say, for example, we see log index 3 of something. And all this means, this word log means to go to this table. The table that involves exponential functions base 3. Go to this table and read it in reverse. That's all this means. Log base 3 means to go to this table, and whatever is in here, like maybe there's an 81. Okay, well, here it is. I got to go backwards. The answer is 4 because I looked it up in my table, right? So you either have these things memorized, or you have a table in front of you, or you have technology in front of you. That's really it. There's no other way to really get the answer to this unless you have a table or you have it memorized. Good. We see log index, and the index of the log is log index 5. We know to look at this table, right? And so now, in order to get this answer, say if I see a 125 in here, 125, then I know that, okay, I got to go to this table because it's index 5, so I got to take this table and read it in reverse, and that's how I know that the answer is 3. Good. Any questions at all? Kind of? Maybe? Sort of? I don't know if it's demystifying logs. Log index. So notice that some of these numbers are the same. I didn't put any of those in here, did I? So for example, note that log base 8 of 64, that means to go to this table. Oh, here's 64, read it backwards, so that must be a 2, right? And for the same reason that it's just reading this table in reverse, then we can also take each one of these statements and say that it must also be true. If this is true, log base 8 is 64, that's reading this backwards, the answer is 2. It must also mean that 8 squared equals 64. Right? So there's this little circle of life that happens here. Start by looking at the index of the log, and then you go over here, raise it to that power, and it must be equal to this. Right? Just like over here, this raised to that power must be equal to this. This raised to this power must be equal to that. Right? So 3 to the 4th power must be 81. And 5 raised to the 3rd power must be 125. Good? Any questions at all? No? No? Maybe? Sort of? Maybe? Sort of? Okay, so next we're going to start thinking about the graphs of these, right? So this is a brand new function. So we have, let's focus on this function with the square. Let's push this down over here somewhere. Get away from all that mess. All right, so we had the function f of x equals x equals to 2 to the x power. So we can have a new function which reverses this process, right? The inverse. Inverse was going to be log base 2. And now if we leave it blank, we know that it goes in reverse, right? Here the inputs are these numbers. They go in here. The outputs are out here. Now these outputs go into the input here, and they give you your output. So we can consider this a function. Now we just keep using the letter x. It's just common. We use it way too much, but it's whatever. It's the input of this function. And because they're inverse functions, we like to denote them with this little -1 up there to indicate that they're inverse functions of each other. They're related to each other. So if we wanted to graph these, we know that all of these would make ordered pairs. Right? And then if we wanted to graph its inverse, well, the range of this function becomes the domain of this function, right? Since we're just reading this function is just to go backwards, right? These become the inputs and these become the outputs, right? In this direction, this is the domain and this is the range in this direction. But when you want to go backwards, then for this function, the log function, this becomes the domain and this becomes the range. So all the ordered pairs of the graph have this as an input and this as an output. So for f of x, for example, we have the ordered pair 5, 32. And for its inverse function, the log function, inverse of x, they'll just be reversed. This would be 32. Let's put it in red. We'll have, for the inverse function, f inverse of x, we'll have 32, 5. Right? Since we're just reading it in reverse, if we input 32 into this log function, its output would be 5, since we're just reading it. Okay, so we're really just swapping around the inputs and outputs. And we learned from our previous study of inverse functions that when we graph them, we get a special property that comes out of all of that. Okay, we're doing okay? Maybe? Questions? All right, so let's go back to this guy and look at graphs. Okay, so graphs of logarithmic functions. Okay, so we know that if a one-to-one function f has domain A and range B, then its inverse function f inverse has domain B and range A, right? They flip-flop, right? All the inputs become outputs, so the outputs become inputs. They undo each other, so their domain and range swap, right? For an exponential function of the form a to the power of x, where a is not 1, and remember a has to be a positive number, so it's got to be greater than 0, but not 1, has a domain R and the range from 0 to infinity, right? Remember that all of these graphs, all of these functions here, have the two general forms, right? We have either this general shape, it goes like this, or we have another general shape that goes like this. Right? This is all functions that have the form a to the power of x have either this shape or this shape, right? And this shape will happen whenever a is strictly greater than 1, right? So for example, 2 to the x power would look like that, and 3 to the x power will look like that, and 10 to the x power will look like that. The bigger the base, the steeper this climbs toward infinity, and the faster this goes towards 0, right? And it doesn't have to be whole numbers either. It could be decimal values, so it could be 2.7 to the x power. It could be e to the x power, as we've seen. right? So all of these have this sort of shape, and they all go through this point, which is the point 0, comma 1, because any whole number raised to the power of 0 is going to be 1. Okay, all functions that have this shape are going to be cases where the a is strictly greater than 0, but strictly less than 1. Some decimal number trapped between 0 and 1. For example, 1/2 to the power of x, or 0.37 to the power of x, right? They'll have this sort of a shape. They will still have the point 0, comma 1. All of them will have that, right? And then, of course, depending on the actual decimal value, they will go a little steeper toward infinity on this end and still go toward 0 on this, right? So for both of these, the domain and range are both the same though. So for this one, the domain is still all real numbers. Domain is all real numbers, right? We like to denote it like that. And the range is positives, right? From 0 to infinity. Not including 0, so put a little parentheses there, up through infinity. For this one, it's going to be the same thing, right? The outputs are a little bit different. The shape of the graph is different, but the domain and the range stay the same. The domain is all real numbers, and the range is from 0 to infinity. Good. Questions, 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 questions? No? 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 Okay, so if we have a function that's going to reverse all the inputs and outputs, right? It's inverse function, then the inverse function is going to flip these things around. It'll be a new function where the domain is from 0 to infinity and the range is all real numbers. Right? That's what we're driving at here. The exponential function has a domain of all real numbers and a range of 0 to infinity. We conclude that its inverse function, which is the log base a of x function, is going to have a domain of 0 to infinity and a range of all real numbers. Good. And remember that from our previous study of inverse functions, the graphs of inverse functions have this property. Right? They reflect, they're a mirror image about the line y equals to x. So as we think about the graphs of the log functions, they're going to have two general shapes. Let's put it in green over here. If we think about the line y equals to x, which is this little dotted line here, here's the line y equals to x, then its mirror image about that will be the log function, and its mirror image is going to have a shape that looks like this. Right? These two are mirror images of each other. So this is going to be the function log base a of x, as long as a is bigger than 1. So here's a better graph of that. So this is when we have a is greater than 1. So we have this as a to the x power. They all have this shape. And then its log function has this as long as a is greater than 1. Right, this is the line y equals to x. So the fact that, okay, very rapidly increasing function x implies that log base a of x is very slowly increasing. Right, so here the a to the x power function grows very quickly. So its inverse function is going to grow very slowly. This approaches 0 as x goes toward infinity. And so this one will approach the y-axis as x approaches 0. Right, so this red line is never going to be equal to the y-axis. It's never going to cross across the y-axis. It's going to get infinitely close as x gets infinitely close to 0. But x could never actually be equal to 0. Good. Here this point exists for this function, 0, 1. any base number a raised to the power of 0 equals to 1. So its log function is going to have the opposite, right? We're just flip-flopping these, so that it'll be 1, 0. Questions? Okay, it says sketch the graph of log base 2 of x. Well, we've kind of already done that. We have a nice table for it, and if we just flip-flop all those values, we'll get a nice sketch of it. But as long as we're using technology, let's see what it looks like with Desmos. Desmos.com. All right, so let's pretend we don't know what it looks like. So we begin by creating a graph that has 2 to the power of x. So like negative, there's a 0 gives you 1. There's that dot right there. Let's put it in blue. Okay, so there's 0, 1, and then we can raise and then 2, 4, and then 3, 8, which is already off grid. But there we go. Right. So this is all the ordered pairs that we get when we get 2 raised to the power of that input. Maybe raise that to 4. That already goes way out of screen here. Oops. So let's go. That makes it all the way over there. Okay. We can also have some negative values. So negative 1, negative 2, negative 3. Right. And again, we start to see that general shape of a to the x power when a is greater than 1. Good. Okay, so we already know that that's what the graph looks like. So let's graph 2 to the power of x. Put it in blue again. So if we kept going, putting in values, we can fill in lots and lots of ordered pairs. Eventually, all those ordered pairs will begin to look like a nice, smooth curvature. So we say that this is the curvature that represents all solutions to 2 to the x power. Okay, so now if I create a new table, and all I'm doing, let's begin by just reversing all of these. I know that the reverse function is just going to have this. Can I just graph a value about 1? I'll just type in this. Can I just put, yes, it works. Okay, so let's put it in red. Okay, so I know that the original function has the point 0, 1. So I know that reversing these, the inverse function should have 1, 0. If the exponential function 2 to the x power maps 0 over to 1, then its inverse function should map 1 back to 0, right? So we get that point. Let's try another one. Going backwards, we know that 16 should map back to 4. So we should get this one, right? So if this function maps the 4 over to the 16, the inverse function that will undo this process, reverse it, inverse functions, should map 16 back to 4. So when we input a 16, we should get a 4. We get that dot. Okay, so we can just go backwards to all of these and create ordered pairs. 2 should map back to 1. 4 should map back to 2. 8 should map to 3. Point 25 should map to negative 2. 0.125 should map to negative 3. Okay, and you start to see what the graph should look like, right? Again, we can graph the line y equals to x, and we see that its inverse function is going to be a mirror image reflection about that line. So if we keep going with these red dots, keep going, eventually we'll see that it begins to map out this. So we need y equals, and I need the log function. That's got to be over here. Oh, there it is. Log index 2 of x. Looks like that. Any questions so far? No? So this is 2 to the x power. This is log base 2. Good, 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 good. Okay, so let's do the same thing where the base is somewhere between 0 and 1. So let's see what this looks like when this is equal to, I don't know, about a half. Get rid of all of this. So we're going to repeat the same process, except this time we're dealing with, let's say, 0.5 to the power of 2. Okay. Oops, the power of x. Okay, so when we want to have 1/2 to the power of x, so 1/2 to the power of 0 is still 1. 1/2 to the power of 1, well, that's just 1/2. 1/2 to the power of 2 is 1/2 times 1/2, which is 1/4, which is equal to 0.25. Okay, so that's where we get all these points, and we start to see the general shape of an exponential function that has a base value between 0 and 1. Right, and we can always add a little more. I feel like we need a little more. How about -4? -4 gives you that guy. We can also add some more values this way. How about a +5? How about a +6? How about a +7? Okay, so we start to see the general shape of an exponential function that is 1/2. Let's put 1 divided by 2 power of x. 1/2 to the power of x. And so after a while, we begin to see that shape right there. Good? Questions, 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 questions? No? No, no, no. Okay, so now if we start to go backwards on these, we just kind of blindly copying these, and we know that the inverse function should undo this process so that 1 should map to 0. Okay, we already have that one. And let's get rid of these. Okay, so that means that just kind of blindly following these, this function that will reverse this process should map 0.25 and map it over to 2. Okay, we should get these 2 points. Here, the original function mapped 0 to 1, so therefore this function should go from 1 to 0. Good. And then this point over here, we have 0.25, comma 2, and that should be the opposite of this one. No, this one. 2 comma 0.25, 0.25 comma 2. Okay, so kind of blindly going through and copying more of these things. 0.125 and 3 and 0.0625 and 4. We see that as x gets closer and closer to 0, this function seems to be going that way, right? Getting closer and closer to the y-axis. And as we go in this direction, so 2 should map over to -1, and 4 should map over to -2, and 4 should, and 8 should map over to -3, and 16 should map over to -4. You start to get a sense of what this graph will look like. Right? Again, we can graph our line y equals to x, and we see that it should be a mirror image about that line. Good, so let's put 0.5 here. Okay, so I can't do that. Y equals 2 functions miscellaneous log index 0.5 of x, and let's make it red. There. Okay, so this red line here is log base 1/2 of x, whereas the blue one is 1/2 raised to the power of x. Good? Questions, questions, questions? Notice that the domain of the blue one, the domain is all real numbers. The output is positive real numbers, right? Anything greater than 0. On the other hand, for the red function, the domain is positive real numbers greater than 0. Those are the only inputs you can put into the red function. And the outputs are going to be all real numbers, right? This goes out toward infinity that way, and this will continue to grow this way, and it never tapers off. It just is growing down toward negative infinity. It's just growing slowly. Questions? No? Maybe? Kind of? Maybe? All right, let's leave this. All right, so we kind of answered that. Right, we can create a table and find some values and graph them, and we get a general sense of the shape of log base 2 of x. And then here are various logs. Log base 2 of x, log base 3 of x, log base 4 of x, log base 10, right? So various shapes of logs. And they are all, again, the mirror image across the line y equals to x to the function 2 to the x, 3 to the x, 4 to the 5 to the x, 10 to the x power. Any questions about these? No? Right, you can draw them all by drawing the line that's a mirror image across the line y equals to x to all these exponential functions. 2 to the x, 3 to the x, 5 to the x, 10 to the x. Good, good, good. All right, what would this be? Negative log base 2 of x. And so just kind of work our way through a sketch, a rough sketch of what this is. So first of all, if you're not really sure, I think it makes a little sense to begin by thinking about f of x equals to 2 to the x, first of all. Right, that gives you some sense of what the graph will look like. So this graph begins this way. I know it's going to have this sort of a shape. Okay. And then if I think about the line that reflects across that one, I'll get to log base 2 of x. And a really ugly equation. So this one here is the inverse function, which is going to be of x, which is log base 2 of x. Okay, so now the only thing is this minus here. What happens when we multiply the output of our function by a -1? It's a reflection about the x-axis. Right? All previously positive numbers are now going to become negative numbers, and all previously negative numbers are going to become positive numbers. So it's a mirror image reflection about the x-axis. Good. So here I'm sure they have a nicer picture over here. Here. And so here is our log base 2 of x, right? Which is a mirror image across the line of y equals to x of this function over here that goes this way. Here's 2 to the x power. Its mirror image reflection is log base 2 of x. And now if we do a reflection about the x-axis, we get this red one to be our final solution. Any questions? No? Maybe? No? What about this one? How is this one related? Well, again, we start off with 2 to the x power. Then we can get to log base 2 of x is this one. And then this one we know is a mirror image reflection about the y-axis. Right? Should have labeled it. This is our y-axis. Here is our x-axis. So it should be something over here that's a mirror image about the line, about the y-axis. Good. I'm sure there's a nice picture of it down here somewhere. Here. Good. So if we think about the line y equals to x, which goes across this way, here's y equals to x. We have this exponential function that goes this way, like this. This is 2 to the x. Its mirror image would be over here, which goes this way. And then if we reflect that about the y-axis, we get to this one, which is what we were asked about. Log base 2 of negative x. Any questions? Okay, so from the graph you can see that the domain of the function h is, the domain becomes negative infinity to 0, and its range is still all real numbers. Good, 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 good. Any questions? No? No? Okay, common logarithms. Common logarithms, or the common logarithm, is logarithm base 10. So just like with roots, square root of, index 2 in the roots, index 2, this thing is so common, so popular that we just ignore it. And by default, if there's nothing written there, we assume it's a 2, right? So square root of 64, we assume that that's a 2, and that's how we know that the answer should be 8. Okay, well, same thing here. By default, if you don't see a little index to our log, by default, it should be a 10, right? We have a base 10 number system. 10 has got a lot of nice properties to it. So by default, we like to work with 10 pretty often. So if you don't see a little index, it means base 10. And so log of 10 means that there's a little index here of 10, right? And the reason this is a 1 here is because if we have a little base here, 10, well, I shouldn't put it in. If we have a little base 10 by default in there, then this is telling you that this raised to this power must be equal to whatever's in there. So 10 to the first power is 10. And then for a little 10 there, then 10 raised to the second power is 100. That's true. Okay. And then, well, what if they're not whole number values, if they don't work out quite as nicely? So if we have a log base 50, then we really want to ask ourselves, right, when you see this, when you see log log of 50, man, it's ugly. Log of 50, all right, so by default there must be a little 10 here. Since there's no index, that means I can just insert a little 10 in there. And when they're asking you what this means, equals question mark, right? In your head you should be thinking 10 to what power, what exponent can I raise 10 to in order to get a 50? Now it might not be a nice whole number like here, 10 to the first power was 10, 10 to the second power was 100. So it might not be a whole number value, there might be a decimal value. 10 to what decimal value equals to 50? So even if we don't really know the exact answer, we kind of have a sense of what it should be, right? It's somewhere between 1 and 2. Just like roots, right? We know that the square root of, let's go back up here. We know that the square root of 64 is 8. We know that the square root of 49 is 7, right? But what's the square root of 53? Right, like, I don't know, it's not a whole number value. It's some decimal value somewhere between 7 and 8. All I know is that it's got to be some number so that when I square it, it equals to 53. Right, that's what this is saying. The answer will be something, I don't know, a, but I know that the special property of this number is going to be that when I take a and I square it, the answer will be 57. Sorry, 53. Such that when I square whatever answer that is, I should get 53. Good. So same thing happens here. I don't know what the answer is. It's some decimal number. It's bigger than 1 because 10 to the 1 power is 10. It's smaller than 2 because 10 to the second power is 100. So it's some decimal value between 1 and 2. And of course, I don't know how to get that number exactly. I conceptually can understand what it's trying to give me. I can leave it as a representative decimal with the notation log of 50, just like we do with, say, we often work with, say, root 3. I don't know what that is. I know it's some decimal so that when I square it, the answer is 3. But since I don't really know the decimal, I can just leave it like that, and this represents that decimal. So here we could just leave it like that. Log of 50 is a decimal. It's some decimal that has a certain property, the property being that 10 raised to the power of this decimal equals to 50, right? 10 to the power of whatever this decimal is, log of 50. Whatever this decimal is, it has the property that 10 raised to that decimal is equal to 50. Right? Good. But we can use technology to get an approximation. So let's just go over to your calculator so you can see where that button is. So logs are really popular, and we have nice, easy buttons for logs. So wherever you're at, let's quit out of there, clear. And here we have a special button just for logs. And the common log is very, very popular. So we have a special button right here that just says log. And by default, whenever you see log, it's base 10, right? So let's just try some obvious ones. Log of 10, the answer should be 1, right? Yes, 10 to the power of 1 equals to 10. And log of 100, the answer should be 2, right? 10 squared is equal to 100. Good? Okay, so this guy's working. So now if we just put log of 50, it'll give us a nice decimal approximation, right? And what's special about this decimal? This is the decimal such that if we take 50 and raise it to the power, clear. If we take 10 and raise it to the power of this decimal, approximately 1.698970004, 10 to the power of this decimal should be pretty close to 50. Some rounding issues, but it gets pretty close to 50. Good. So 69.89.7 is the answer. Log base 50, 1.698997. Right? And that's the decimal that belongs here. We knew that this had to be bigger than 1, but still less than 2, and it agreed. It's bigger than 1, but still less than 2. Any questions? No? 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 As long as we're using a calculator, we can graph our log function, and we can use the values to sketch its graph. Right? So I think that this is probably an overkill. We've already spent a lot of time on this, so I think we could do that. Use a calculator to find the approximate values of log 10, and then use these values to sketch its graph. Okay, so I'm going to just skip on over to the answer to this thing. I don't think we can answer this if we wanted to. Okay, so we can create a table, right? Log base 10. We can use our calculator to create these values. And then no surprise, it has the same shape as all the other ones. Base 2, base 3, base 10, it still has the same sort of shape, just different specific values depending on the table. Any questions? Any questions? No, 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 no. Okay, the natural logarithm. Another one that is very, very popular, very important, is to use base e, right? Remember, we developed that number e just a few sections ago. It is the limit, right? The limit as n goes to infinity of the function 1 over n, right? E is equal to the limit as n goes to infinity of 1 plus 1 over n raised to the nth power, right? And what this notation meant was that we replaced the n with a 1, replaced the n with a 2, replaced the n with a 3, replaced the n with a 4, dot, 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 dot. So as we kept going and eventually plugged in very, very large numbers for n, and then raised it to the power of this very, very, very large number, we saw that this thing started to approach, right, as n goes to infinity, this thing started to approach a decimal value, 2.7182, dot, 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 dot. So wherever this was approaching, this was the number e. We'll spend more time with this notation down the road. It's kind of a rough introduction at this point. There'll be more specific definitions of what this means later, but hopefully we have a good sense of what that means. Okay, so that number was special. There's a lot of great reasons for why we use that number, and so we develop a whole new notation for it. So log base e is called the natural logarithmic, and it's denoted by ln of x, right? So log base e of x is ln of x. I say we develop a new notation for it because it's special. That's not quite it, right? I mean, math is not developed in a laboratory. It's not like we sat down and thought about how to develop math. Math is, a combination of ideas from different people and different cultures all around the world, everyone kind of contributing. Sometimes they're collaborating. Sometimes they're not really collaborating. Sometimes they're competing. Sometimes they're not even alive at the same time, and they kind of pick up on each other's work. So there was some great mathematician that was doing work on this area of math. And when you're the new person developing an area of math, new ideas, you have to kind of invent your own notation for your ideas. And so sometimes one style of notation is used to express an idea. Somebody else is thinking of the same sort of ideas related. Sometimes you don't even know that they're related, and you come up with your own style of notation. And then it takes a while before people kind of realize these two things are kind of related in one way or the other. At any rate, that's one of the big hurdles in math, that we'd end up having lots of different styles of notation to express similar ideas. You'll see a lot of that in calculus. There's a lot of different notation styles that we have to adopt that are all related to each other, kind of adopted by different mathematicians at different times in different cultures and different languages. And over the centuries, we've kind of slowly molded it into one little packaged up deal. But it largely depends on your author and stuff. So ln of x is a notation style developed by somebody in a particular area of math, and it involved this number here, this e value, whereas this notation of log was developed by somebody else, and well, we kind of blend them together, and so there are authors that often use ln of x, and there are authors that really like to use the log notation. So we just kind of have to be aware that they are similar to each other. Right? So both of these are related to the exponential function base e. So if we have f of x equal to e to the x power, and we want to go backwards on this function, well, that would be this, log base e of x or ln of x. They both mean the same thing. Any questions now that I went off on that little rant? No, no, no? Okay, so we have e to the x power having its usual shape for any exponential function base a to the x power where a is greater than 1. Remember, you can always think about this as like 2.7183 approximately. And so its inverse function is going to be a graph that's a reflection about the line y equals to x. So this red one represents its inverse function, noted as log base e of x or ln of x. Good. And as usual, this is true only if it's true that e to the y power equals to x. Right? Remember the little circle. This is the same thing as log base e of x equals y, right? This thing is ln of x. Same thing. And so the little circle, e raised to this power must be equal to that. And that's how we get this. Any questions? No? No? Okay, so all the same properties that apply to logs apply to log base e, since it's just one of those iterations. Right, so we had a whole table yesterday that showed some of the properties of log base a, and all of those properties apply to log base e, and therefore they can be rewritten in the form of ln. Right, so here's a table consisting of those properties. Right, what does this mean? Remember, this is log base e. Log base e of 1 equals to 0. Log base e of 1 equals 0. That's true. E to the 0 power equals to 1. That's true. Log base e of e equals 1. Right? That's true. E to the 1 power equals to e. Right? And that's how we get this one. E to the 1 power equals to e. Yep, that's true. Whenever we have it this way, well, this is kind of an obvious thing. If we have log base e of e to whatever power this is, let's make it a happy face. E to what power equals to e to the happy face? That's what this is asking. Well, obviously, happy face. E to the happy face equals whatever is in here. So whatever is in here must be a happy face as well. Wow, that's the ugliest happy faces ever. This raised to that power must be whatever's in there. Good. So that's why this is true. E to the x power equals e to the x power. So ln of e to the x equals x, right? Another way to think about it is the ln function and the exponential function base e are inverses of each other. They undo each other, therefore it must be equal to this. Good. And we covered this one yesterday as well, where we had something like this. A raised to the power of log base a of whatever's in here. Let's make this one a sad face. Log base a of sad face. And then we take that and have a raised to the power of that must be equal to the sad face. Right? You have to kind of think about why that is. This, right, conceptually, what this means is that this represents some decimal value so that a to the power of that decimal equals to a sad face, right? So kind of hold that in your head that this must be a decimal, right? This equals some number. Just like root 3 equals some decimal. I don't know what that decimal is. So rather than writing down the decimal, I can just write this notation representative of that decimal. Good. So it's a decimal that exists so that when I square it, it equals to 3. That's why if I square this whole thing, it equals 3. Right? Okay, so this is representative of some decimal. There is some decimal out there so that a to the power of that decimal equals this sad face. Now take a and raise it to that decimal. What does it equal? Well, by definition, it equals the sad face. Okay? Or you can think of these two as undoing each other. And that's how we get this property here. E to the ln of x equals to x. Any questions about that? Kind of, maybe. Okay, what's this going to be? Ln of e to the x. Remember, e to what power equals to e to the 8th power? Well, it's got to be an 8, right? E raised to this power must be equal to this. And there's a little e there. So e to the 8th equals e to the 8th. Yep. So that must be an 8 there. Good, good, good. Pretty good. Okay, to answer something like this, why don't we manipulate this a little bit first to rewrite this as ln of e to the negative 2 power, and then it becomes similar to the one right before. E to what power equals to e to the negative 2? Well, it's got to be a negative 2. Good. And here, well, we can just approximate. I think it's just letting us say use the ln button in our calculator to find this answer. But whatever this decimal is, some decimal number, it's got to be something so that e raised to that decimal number equals 5. Good. So we can just use our calculator, and the natural function is so popular that it also has its own button on your calculator. And these are typically the only two easy buttons on any calculator. So we had this button that has log, remember that's base 10, and then ln is also on there. So for example, ln of e, that should be a 1, right? E to what power equals to e? That's got to be a 1. Good. And ln of e to the 2nd power. Well, let's make it 3rd power. If I have e to the 3rd power, ln of e to the 3rd power, that's just got to be 3, right? Or I can turn it into a decimal. I can say, what is ln of? Okay, e to the 3rd power, that equals to that ugly thing. So now if I take ln of 20.08553692, e to what power equals this decimal? Well, it should be approximately 3. Good. Okay, so now we can find the answer at ln of 5. E to what decimal equals to a 5? I know it's got to be bigger than 1, because e to the 1 power is 2.718, right? And I know that it's got to be less than 2, because 2 to the e to the 2nd power is 2.718 squared, and that's got to be bigger than 5. So here's our answer. 1.60943791 dot 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 dot. And if it works, then it should have the property that e raised to the power of this decimal should be pretty close to 5. 1.60943791 enter. Pretty close to 5. Good. Questions, questions, questions? For what, 38, I guess? Any questions? Questions? 9438. Okay. Right, and that's because e to the power of 1.609438, oh, that's really bad, equals to approximately 5. Approximately. Any questions? Any questions? Any questions? Okay, find the domain of this function. All right, so the domain of this function, we know that this is base E, ln base E. We know that the general shape of this graph should have a shape that kind of fits this form like this, right? ln of x should look like that. So the domain has to be all positive values, real numbers. So whatever goes in here, whatever this input is, it has to be bigger than 0, greater than 0. Good. So that's what we do. We have to set that up and solve for it. 4 minus x squared has to be strictly greater than 0. And now we solve for our values. Okay, so what we have to do is factor this. We end up with 2 minus x times 2 plus x greater than 0. And I have to figure out what values of x produce this. So I would do this by the method where we put 3 number lines all above each other. So here is 0 on the number line, here's another number line, here's another number line. So here we're going to only consider 2 minus x. Here we're going to consider 2 plus x. And here finally we're going to consider the multiplication of 2 minus x times 2 plus x. Okay, all right, so what we want to do is think about what value of x would give me a 0, and so 2 minus blank, that would be a positive 2. So if we put a positive 2 here, this would be the 0 for this value there. And then if you go bigger than that, if we put a 3, a 4, a 5, a 6, we end up getting negative values over here. Right, here's our 0. And if we put values over here like 1, -1, -2, -3, all those values, for this, we end up getting a positive answer. Right? 2 minus 1 is 1, 2 minus 0 is 2, 2 minus -1 is positive 3. So they're all positive values in this direction. Good. Okay, now looking at this, the new 0 will occur at -2. Here's -2. Here is where a 0 will occur for this one. 2 plus -2 is 0. And if I put numbers in this direction, it becomes positive. Right? 2 plus 0 is positive. 2 plus 1 is positive. 2 plus -1 is still 1. It's positive. So it becomes positive in this direction. Therefore, it's going to be negative in this direction. Good. Okay, so now we finally think about the multiplication of the two. So in either way, if you replace these x's by a -2, one of them is going to be 0, so the whole thing becomes a 0. So here's a 0. And then if we replace it with a +2, it becomes a 0 as well. For any input of x that's on this side, we end up with a negative times a positive, which ends up being a negative. And then over here, for any x value that is to the left of -2, we end up with a positive times a negative, which is also going to be a negative. And then for any value between -2 and 2, when we multiply them, we end up with a positive times a positive, which gives you a positive. Now we know that for these two to be a positive value, it must be true that x must be a number trapped between -2 and 2, not including the endpoints, because then that would actually give you 0. Okay? So in order for this to be true, this is true if x is less than +2 but greater than -2. Right, so that's our domain. Our domain is going to be this, or we can also write it as -2, comma, +2. Any questions? No, no. Okay, so we get the same answer. Not sure I like the way they... Oh, yeah, go ahead.
Do you mind going back up real fast so I can copy that? Thank you.
Sure. So there's different ways to get this. I like this 3-number line system thing. You know, after you do it a couple of times, you go through it quickly. So I know it takes a long time the first few times. But like anything else, once you get used to it and you kind of get a sense of it, it goes by faster. And also, once you have a more complicated situation, then this gives you a framework from which to kind of break it down into little pieces and figure out the regions when it's positive and regions where it's negative.
Can you explain how did you do the negative and positive on the number line again, please?
Okay, so let me walk through this one more time. First of all, I want to know the domain of this function, right? So I know that the domain of any ln function must have an input that's greater than 0, right? That I can't put a negative number into here. So whatever you choose for x, once we square it, once we take 4 minus the square of the input, this result must be greater than 1. Because if you choose some value, like let's say you let x equal to 5, we'll end up with 4 minus 25, which gives you ln of negative 21. And as we see from the graph of ln of x, there is no such thing as ln of negative 21, right? So let's begin with that. So if we have ln, if we let x equal to say positive 5, and let's say negative, let's say positive 5, x equals to positive 5, then we end up with 4 minus 5 squared, which then gives you ln of negative 21. And we know we have a problem, right? That's undefined. Undefined. All right, so that means that 5 is not in the domain of this function. Okay, so what is the domain? We have to figure out all the values we can plug in. So we have to make sure that whatever values we plug in result in a positive input value to the ln function. To do that, we bring that over and we solve this. What values of x will produce a positive? Next, we factor it. We see that this is a difference of squares. This is 2 squared minus x squared. And if we recall back from factoring, we had this property that if we have, well, we had it normally in the form of a squared minus b squared. If we see something squared minus something squared, then we know that this factors this way, a plus b, a minus b. Conjugate pairs like this, they're both identical except one has a plus, one has a minus. So here I noticed this was 2 squared minus x squared, so it must be 2 minus x times 2 plus x. If we FOIL this whole thing out, we see that we get back to this. Okay, so now it's tempting to say, well, let me separate this into 2 minus x is greater than 0 and 2 plus x is greater than 0. But we don't want to do that. Instead, we want to think about the combination of the two, right? We don't just want to know when is this positive separately, when is this positive. Sometimes they affect each other, right? Because we know that if this is negative and this is negative, then the output is actually positive. Okay, so we want to think of them together. To do that, one way of doing this, and like I said, you might have your own. If you have your own way of doing this from prior math teachers, that's fine. But what I do is break it down into pieces. One number line, another number line, another line. 3 number lines. All of them have 0, right? So this is x, this is x, this is x. They're number lines. All of them at 0, so that all of them lined up against each other. This first number line is only going to take into consideration 2 minus x. That's it, just this one by itself. So here, what kind of an input would give me a 0? That's what I'm thinking. And so the positive number 2, if we input a 2 into here, 2 minus 2 is 0. And then from that point on to the right, like a number 3 or a number 4, if we input any of those numbers, we're going to get a negative. Right? So 2 minus 3 is negative. 2 minus 4 is negative. 2 minus 5 is negative. So it's negative, negative, negative that way. Here's a 0. And then in this direction, we're going to get positives. If we plug in a positive 1, 2 minus 1 is positive. If we plug in a negative 1, 2 minus negative 1 is actually 3, which is positive. So they're all positive in this direction. Okay, so now next I think of a new number line that only takes this little binomial into consideration and nothing else, 2 plus x. Okay, the new 0 will occur when x is negative 2. 2 plus negative 2 is 0, right? Here is the 0 for this one. Here is the 0 for that one. Okay, so to the right of that, just think of any number over here to the right of it, and you can just jump to the easy numbers if you want. Okay, so 2 plus 2 is 4, that's positive. 2 plus 1, that's 3, that's positive. 2 plus 0, that's positive. All of these numbers are positive on this side. And then if we put in values on this side of negative 2, like negative 3, 2 plus negative 3 is negative. Or negative 5. 2 plus negative 5, that's negative 3, that's negative. Negative this way. Okay. Finally, a third number line, again lined up right here, zeros, and lined up right here, negative 2, lined up down here. Well, that's supposed to be lined up. This is where this thing follows down here and becomes a positive 2. Okay, if I think about the product of the two, I know that negative 2, if I replace each one of these with a negative 2, I'm going to get a 0. This is going to be 0. And if I replace these x's, both of them, with a positive 2, the product of the two is also going to be 0. Is that okay? 2 minus blank and 2 plus blank. If I replace both of them with a 2, then this becomes 0, and this becomes some other number, but it doesn't matter. 0 times any number is 0. Or the other way around, if I replace this one with a negative 2, becomes some number, and 2 plus negative 2, that's 0, so the product of the two is 0. Okay, so that's why these two are going to be zeros. Now if I pick any number over here to the right of 2, one of them is going to become a negative number, and the other one is going to become a positive number, and when we multiply them, a negative times a positive equals a negative. Okay. If I pick any value to the left of negative 2 on the number line, I end up with one binomial becomes positive, the other binomial becomes negative, and a positive times a negative equals a negative, so I know all of these values will be negative. And here's the sweet spot, right in the middle, between these two numbers. Anytime I pick a decimal between negative 2 and positive 2, I know that both of them are going to give me a positive number times a positive number, which means the output will be positive. Just to kind of throw a number in there, for example, 1.2. If I replace this thing with 1.2 and I replace this one with 1.2, I know this is going to be positive. 2 minus 1.2 is a positive number. Positive number. And I know that 2 plus 1.2 is also going to be a positive number. And a positive times a positive equals a positive. So I know that 1.2, I mean, I don't know what the answer is, and it doesn't matter what the answer is. I just want to know if it's positive or negative, and it's going to be positive. Any questions about that? Did I answer your question?
Yeah, thank you.
Sure. Anybody else? Questions, questions, questions? No, 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 no. Okay, I think that this is the end of this. So this is another way of looking at it, but I'm not as big of a fan of this, of remembering that this is equivalent to this, and yeah. So I like the number line method, but you can have your own method too. Whatever you learn is fine. All right, let's take a little break. We'll come back at 10 and move on to the next section.
Before we go to break, I have a question.
Oh yeah.
Do you have a date for the next test?
Well, it'll be next week for sure. So I don't know, maybe Wednesday or Thursday is what I'm thinking.
Okay,
and we'll cover up to wherever we stopped this week. So last time we needed 2 more sections at the end of chapter 2 were not covered on this first test. So the sections we did in chapter 3 and this material from chapter 4, wherever we stop this Thursday, will be the cutoff for this second test, and it will be next week. As far as grading the first test, I'm still working on it. It's really hard to grade over the computer. It's so much easier to just have my papers in front of me and flip through them and mark them and stuff. Doing it this way with 50 different PDF files, and some people didn't quite follow the rules, so some people turned in several PDF files, and it's just becoming it's just really hard to navigate the whole thing. So it takes me a really long time. Sorry, but as soon as I get a grade, get it graded, you'll receive the results. Other questions?
That's it. Thank you.
Okay. All right. Let's take a little break. We'll come back. Say around 10 o'clock. We'll move on to the next section. Section 4.4, laws of logarithms. Okay. Remember that a logarithm is not an operational symbol. It's not like addition, subtraction, division, multiplication. It's not that. It's a function. It's a function that is described by the simple process of looking up the table of an exponential function and reading it in reverse. Right? That's all we're doing with a log. So when you see log, when we see log, why does this always jump to the most thick bar? Okay, so when we see something that says log base 2 of 8, we know that this is saying, okay, go to the table that has 2 to the power of x, right? And we got to read this in reverse. We got to find where 8 is on that table and read it in reverse this way. 2 to what power equals to 8? And if you know your powers of 2, then that's how you'll know that the answer is 3, right? The answer is 3. And that's because 2 to the power of 3 is 8. Okay, so for that reason, whoa, how did we get to this? That's cool. Don't know how I jumped way down there. But at any rate, for that reason, there are special properties of logs. It's not an operational symbol, so therefore multiplication, just like multiplication, division, addition, subtraction, those are operational symbols. And properties, say like distribution, exponents, the rules of what we're allowed to do with operational symbols differ from logarithms, right? Logarithm is a function and it has its own special properties. So we're going to look at those properties. Okay? Okay, so laws of logarithms. Here they are, right? So here are some of the most common ones that we're going to use. And I'm not going to go through the proof of them, why they're true. Let's zoom in a little bit more. But let's just describe what they're saying. This is saying that if we have a multiplication of two values, a times b, inside the argument of a log base a, then we can separate this as the summation of two logs. So for property A, this is saying that we could have log base 2 of a multiplication, like let's say it's 3x, right? That's a multiplication. And according to property 1, this is equal to log base 2 of 3 plus log base 2 of x, right? So we can separate this multiplication in here. Multiplication inside the argument of the log can be rewritten as the summation of two logs with the same base, right? We keep that same base in the index of the log. Good. Same thing happens with a similar thing happens with division. If we have log base a of a division of two values, a over b, then that's equivalent to the difference of two logs with the same index of the log. Right? So again, just as a quick little example, if we have log base 2 of some division, maybe that division is x over 3, so there's a division in there. According to this property, this is equivalent to log base 2 of x minus log base 2 of 3, right? So again, we have a division in here, a division inside the argument of the log can be rewritten as a subtraction, a difference of two different logs with the same index and in this order. The value in the numerator of this fraction goes here, the value in the denominator of the fraction goes there. Good. Again, I didn't really prove why that is, but we're just going to use these properties. Good. And then last and probably most important is this one. This is saying that if we have a value written in exponential notation inside the argument of the log, then we can take that power and move it out in front like a linear factor times log base a, so we keep the same index of the exponential number, we write it to the power of 1. So, for example, if this was log base 2 of 8, we can rewrite this as, well, okay, we know that the answer is 3, right? Log base 2 of 8 is 3. Okay, so we can rewrite log base 2 of 8, we can rewrite it as log base 2 of 2 to the third power, right? Because 8 equals 2 to the third power. And according to this property, since this is written in exponential notation, we can take that out in front and write it as a linear factor. So we can rewrite this as 3 times log base 2 of 2. Log base 2 of 2 is 1, so we know that 3 times 1 is 3, so we're going to get the same answer. Right? And that's true no matter what exponential value is in here. It just so happens, just for the purposes of this example, I made this index and this base match, but they don't have to. According to that property, if I have log base 3 of 5 to the x power, then that property says I can take this exponent here, move it out in front like a linear factor, and rewrite this thing as x times log base 3 of 5. Log base 3 of 5. So this is a really important property because it allows us to solve for whatever exponent is in there. Right? So we get to rewrite it as something that does not involve an exponential power. We'll see how that's useful in the next section. But it is a really important property of logs. Okay, remember log is a function, so we have to be careful about the rules we're allowed to use. So use these rules and be careful not to kind of create your own rules. It's very tempting to want to say that things work differently. So for example here, this is the rule. But very often people confuse this. They see log base 3x and they see that there's multiplication in here. So they think that this is equal to log base 3 times log base x. Right? And that's not true. When we have a multiplication in there, then that turns into addition of two logs. Not this way. That's not true. Right? Another common mistake is that people think this works backwards. So if they see log of 3 plus x, maybe it goes backwards and it equals to log of 3 times log of x. That's not true. And also they maybe kind of think that there's some sort of distribution process that happens. So this one's also not true. And then the last, or another common mistake is that people think this is true, that we can somehow distribute this log and end up with log of 3 plus log of x. Some sort of a distribution process here. And again, that's also not true. Right? There is no property that says that you're allowed to distribute a log across an addition like this. So none of these are true. We have to be very careful about what we are allowed to use, right? And that's what this table gives us. 3 properties that are true. If there is multiplication inside the log, it's equal to an addition of 2 logs. Now you can go backwards from here to there, or forwards, right? The summation of two different logs with the same index equals that. But you can't have an addition inside the argument of one log and somehow separate it into, something like this. This is not true. Good? Any questions? Okay, so let's evaluate some of these things. Of course, if we had a calculator, we could do it. This is saying 4 to what power equals to 2. 4 to what power equals to 2, so I think we can kind of guess what that is. And then also this one, 4 to what power equals to 32. So, okay, we can kind of get a sense of what that is saying. But instead, we're going to try and use these properties to combine it as one single happy log, and then from that, get our answer. Okay, so they have, these two have the same index. So that's going to be like property number 1, this one, the summation of two logs with the same index, and that's equal to one happy log with the same index, and then we multiply the arguments of these two logs. Okay, so this is going to be equal to this. This is equal to log base 4, we keep the same index, of 2 times 32, right, which will be equal to log base 4 of 64. Right? And then when I want to find this answer, I got to think to myself, 4 to what power? Remember this little thing. 4 to whatever this answer is, the answer there, 4 to the power of that must be equal to 64. Right? So what is that? 4 times 4 is 16. 16 times 4 is 64, so that's got to be a 3. Good. Questions? Right, this is because 4 to the power of 3 equals 64. Good. Same with the difference of two logs with the same index. According to property 2, if we have a subtraction of two logs, then that's equivalent to one log with a division of these two arguments in this order, and we keep the same index, a in that case. Okay, so in this case it's base 2. This is going to be the same thing as one big happy log, base 2 of 80 divided by 5. Good. Questions? Okay, so this is going to be equal to log base 2 of 80 divided by 5 is 16. And so now when I want to find the answer to this, again, I think to myself, 2 to what power equals to 16? So 3, 4, right? That works. And that's because 2 to the 4th power is 16. Questions? No. Okay, this last one, how do we simplify this? Well, we can use the cube root of this thing to get us to a 2. There isn't going to be a simple, happy little answer, but I think maybe we can just approximate it with a calculator. That's probably the intention here. So we can just use our properties to rewrite this a little bit. According to our third property, we can write the third property. If we have a constant out here, we can rewrite it as a log with this value in the argument of the function raised to the power of this constant out here. So according to that property, this is the same thing as log of 8 to the power of negative 1/3. Good. And negative 1/3, well, that's the same thing as log of 1/8 to the positive 1/3 power. And we know that that's the same thing as log of 1 over the cube root of 8. So that'll be log of 1/2. Good. Okay, so even though I don't really know the answer, I know at least what it's asking me, right? By default, if there's nothing here, there's nothing written here, that means there's a little 10, right? And whatever this answer is, it'll be 10 to whatever that power is, must be equal to 1/2. 10 to what power equals to 1/2? That's what they're asking us. Good. Okay, well, luckily 10, log base 10 is a nice, pretty number on our calculators, so we can just go over our calculators if you ever get stumped with one of these. So let's launch our calculator. So log of 0.5 equals this decimal, right? And that works because that must mean that 10 raised to the power of that decimal, negative 0.3010, let's just approximate it to 3. Pretty close to 1/2. Good. Any questions? No? 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 Okay, let's see what the author did for that last one. Okay, so we had that this must be 3. We got that one. And okay, same thing. So they used the calculator. So we can just stop at this point and go, okay, I've simplified it as far as I can go, log of 1/2. Or if you have a calculator and you want to round it to some decimal value, you can just use technology at that point. Any questions? Any questions? Any questions? No? No? Okay, expanding and combining logarithmic expressions. So we can use these properties to either expand or combine logarithmic expressions, and that can in turn help us solve logarithmic and exponential equations, which we'll do in a little bit. But first, we want to take baby steps and learn how to use these properties to both expand and contract these functions. So use the law of logarithms to expand these expressions. So you want to go in one direction to expand them. So here for this first one, we have multiplication. And we know that if we have a multiplication inside the argument of a log function, that means that we can rewrite it as an addition, right? So for a here, I'm going to have that this is equal to log base 2 of 6x is equal to log base 2 of 6 plus log base 2 of x. Good. Any questions? For b, we have log base 5 of x to the 3rd power times y to the 6th power. So first, we have a multiplication, so we can separate that as the addition of two logs. So this would be log base 5 of x to the 3rd power plus log base 5 of y to the 6th power. And next, we can use our third property to bring that exponent out in front like a linear factor. And so this becomes 3 times log base 5 of x plus 6 times log base 5 of y. Good? Questions, 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 questions? The third one, c, we have ln of ab divided by the cube root of c. And remember, ln is just log base e, so all the same properties apply. we have a giant division here, so this is going to be ln of AB minus ln of cube root of C. Cube root of C is the same thing as C raised to the power of 1/3. So this can be separated as ln of A plus ln of B, right? Because here's a multiplication, minus ln of C to the 1/3 power. And then we can bring that 1/3 power out in front and rewrite this as ln of A plus ln of B minus 1/3 ln of C. Any questions? No? 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 Okay, let's see, that matches what we got. Here's what your author did. Law 1, and then law 3, and then same thing we got. So the logarithms can also serve us to, in the process of expanding, that was done in example 2. That is, we can write sums and differences of logarithms as a single logarithm. So combining logarithms, we can go backwards. So given a long expanded expression like this one, we can use the properties of logs to combine the whole thing into one big happy log. So for part A, let's put it over here. Log A, part A, we can say that we have log base 10, log base 10. They have the same index. By the way, if they didn't have the same index, things would be a lot more complicated. So if this was log base 3 and this was log base 5, things would get tricky. So we'd have to do some other work. We can't just apply this, this property straightforward. So luckily for us, they're both log base 10. Right? By default, if there's nothing there, they're both log base 10. They have the same index. And there's an addition here. So we know by property 1 that this must be equivalent to one big happy log. Wait a minute. That property, though, applies to the summation of two logs. Notice that there is no constant out in front. So let's go back over here. Where's that property? Oh, here. Notice that when we apply this property, there's a constant of 1 out in front of log base A of A and a 1 in front of log base A of B. So if there's something in front there, we're going to have to use property 3 first to rewrite it like this and then go backwards. Right? Okay, let me illustrate what I mean by that. So a common mistake is to take this and, here, let me just copy it over here. We have 3 log of x plus 1/2 log of x plus 1. Okay, since we see addition, people usually notice that that must mean some sort of multiplication of the two. So that, oops, I put an L in there. Log of this. Okay, so it's got to be log of something multiplied by something, right? Something multiplied by something. And it should be this something times that something. But what about the 3 and the 1/2, right? How does that work into this whole process? So before you jump into this, we're going to have to rewrite this without those coefficients out in front. And we do that by using property 3. We're going to take these guys and move them from here and into the exponent of there. Good? Okay, so we're going to first rewrite this as log of x to the 3rd power plus log of, and now you got to be careful because it's the entire thing raised to the 1/2 power, not just the 1, not just the x, but it's x plus 1 raised to the power of 1/2. Okay, now we're ready to rewrite this as one big happy log of, and it's x to the 3rd power times x plus 1 to the 1/2 power. Any questions? Questions? No? Okay, looking at B, let's move this down here. B, we want to do the same thing. We have 3 ln s plus 1/2 ln t minus 4 ln t squared plus 1. So we want to take all these exponents, and all these constants, coefficients out in front, and move them into the exponents. And then we'll be able to deal with the addition and subtraction properties. Good. So then this is equivalent to ln of s to the power of 3 plus ln of t to the power of 1/2 minus ln of t squared plus 1 raised to the power of 4. Good. And now these two, because we have an addition, combine into ln of 5 to the 3rd power times t to the 1/2 power minus ln of t squared plus 1 raised to the 4th power. And now we have a subtraction, so these two divide. And so my final result for B equals that, and so my final result will be ln of 5 to the 3rd power times t to the 1/2 power all over t squared plus 1 to the 4th power. So that's pretty good, but you might want to expand this, right? So the rule of thumb here, the guideline is that if this exponential number turns out to be a number less than 1,000, we usually like to see it expanded. Otherwise, leave it as an exponential. So you might find this final solution to be 125. Also, fractional exponents, if it's a simple one like a half or a fourth or a third, people usually like to see it as a root notation. But if it's a different one or more complicated, we like to leave it in a fractional exponent. So it's pretty common to see this way. 125 square root of t all over, and then this one we definitely don't want to expand, right? So t squared plus 1 to the 4th power is pretty ugly, so we leave it alone. Any questions? No? We're good? Expanding and contracting using our properties? Expanding and combining. Okay, so we did that one, we got that, and we got that. Right? So author got the same thing. Okay, so we can use these properties in various applications. So here's one application of logs. In social sciences, we try and come up with a model that describes how long it takes people to forget information. So if a task is learned at a performance level P0, right, then after a time interval t, the performance level P satisfies this equation. Okay, so P0 is some sort of metric to gauge how well you understood a given task. T represents time. C represents some constant that is special to that task. And then P is your performance level after T time has gone by. Okay, so part A says solve for P. So let's first of all just use our awesome properties to solve for P for part A. We have log of P equals to log of P0 minus C log of t plus 1. Okay, what I want to do is combine these two into one big happy log, since they're all log base 10. Right? We're trying to solve for P. Remember, I can't just, this is a very common mistake. You go, okay, solve for P, people do this. Log cancels, and log cancels. Right? That's not true. There's nothing in the properties of logs that say that you can divide by log. That doesn't make any sense at all. That's kind of like saying if I have square root of x equals to 1 plus square root of, 8, that somebody comes in and says, I know how to solve for x. I'm going to divide by square root, divide by square root, divide by square root. I'm like, what in the world is that, right? This notation is meaningless. This function needs an input, and that's the same as this. Just dividing by log is meaningless. You might accidentally get to the right answer. That happens sometimes, but that doesn't mean it makes any sense. Good? Okay, so we don't want to do this. Any questions about this at all? Right? Okay, so we don't want to divide by nonsense. That doesn't make sense. Okay, so what are we going to do? Let's combine these things into one big happy log. Oops. Let's go back over here. So we have log of p equals to log of, and this is going to be a division, right, because of the subtraction. And what I'm going to have to do is take this exponent, this constant, and raise it into the exponent of that guy. So I'll end up with p naught, and then here we end up with t plus 1 raised to the power of c. Good. Okay, now we can say that p must be equal to this, right? Because we have log of this equals log of this, so therefore these two things must be equal to each other. Good? Questions, questions, questions? Like if I have the square root of, x plus 1 equals the square root of 25, then I can conclude that x plus 5 must be equal to 25. Good. Or the other way you can think of this is that we can raise both this way. We can say that this is 10 to the power of log p. So we apply this into the function, to the function 10 to the x power. And we do the same thing to the other side, 10 to the power of log of this, p naught over t plus 1 to the power of c. Right? Either way, these two operations undo each other, and we end up with the statement that p must be equal to this, t plus 1 to the c power. Okay. Any questions about this? No? We're okay with it? Good? Okay, so if we're trying to solve for something, and it's kind of buried inside a log function, and we can simplify it and get it to a point where log of something equals to log of something, they're the same index, the same index of the logs, then those two arguments inside those logs must be equal to each other. Right? So that's the general rule that we have. Log base a of x equals log base a of y. Right? If this is true, log base a of x equals log base a of y, then we can conclude that x must be equal to y. Good. This also applies to, for example, if 2 to the power of x is equal to 2 to the power of y, if they both equal each other, then we can conclude that x must be equal to y. Good, good, good. Okay, so part A said solve for p. We did that. Going back to this word problem. We have this weird function here, this weird expression that expresses the relationship between how long it takes for you, the retention of knowledge over time. Right, so then part B says apply it. We have, if your score on a history exam is a 90, so that's your initial level of performance on this history test, that would be P naught. So we're saying P naught equals to 90. What score would you expect to get on a similar test after 2 months and then maybe after a year, assuming that the coefficient, the constant coefficient value for this type of a task is at 0.2? Right? Okay, so the values are all given. This is saying P naught, from here we get that P naught must be equal to 90, and c equals to 0.2, and we want to know what's going to happen for different t values. We have t equals to 2 months, and also t equals to 1 year, so t also equal to 12 months. Ignore that number there. So that's what we want to know, right? And then p is the question mark. So we solved for p, so all we have to do is plug and chug now. So for t equals to 2, then we have that t equals to p naught, which was 90, over t, which is a 2, plus 1 to the power of 0.2. And this will give me my answer. And for t equals to 12, that's not a 12, 12, then p equals to 90 divided by 2 plus 12, 12 plus 1, I should say, to the power of 0.2, and this will give me my answer. Okay, so this is going to be 90 divided by 3 to the power of 0.2, and this is going to be 90 divided by 13 to the power of 0.2. Okay, we can use our calculator and get an answer from there. And let's just see what the answer is over here. Okay, so they got the same result as I did for solving for p. Now when you plug it in, you get these. After 2 months, t equals to 2. That's 90 over 2 plus 1 raised to the power of 0.2. So after 2 months, you would expect that your score should be around 72. And after 1 year, your score should be somewhere around 54. Right? If you don't use it, you lose it. So even though you had learned this material up to a proficiency of about 90, after a year of not working on this, not thinking about this, if you were given a similar exam, your score is expected, according to this model, to be in the neighborhood of 54. Good? Any questions? No? Okay, so you might have noticed that so far in our calculator there were only 2 easy buttons. There was a button that had ln, and there was a button that had log. Right? So this one by default is base 10, and this one is base e. But what about everything else? What if I wanted to find log base 7 of, I don't know, 13? What is it saying? This is a decimal, so that 7 to the power of that decimal equals to 13. How do I find that on my calculator? Now, some of you guys do have a button on your calculator that lets you type in this exact thing right here. It lets you type in the index of the log. So I'll show you where that is in a second. But for you guys, when you see that button, it'll do this, and then it'll be a little blinking box right in there. And then you can stick in a 7 right in there, and then stick in the 13 right in there, and then that'll give you your answer, and you're good to go. But what about everybody else? What if we only have these 2 buttons? Well, luckily, it actually doesn't really matter very much. There's an easy way for you to change the base of any log function, and that's with this knowledge. So let's say that you're asked to find this. What is y when it equals to log base b of x? And let's say b is not a common function, log base 7, right? So this one's saying, what is log base 7 of x? What is log base 9? And that might not be a button on our calculator, right? Okay, so by definition, oops. Whatever. By definition, remember this must mean that b to the y power equals to x. Usually I see it written, usually we've had it written in the other direction. So let me just flip it around. Right, so by definition, this must mean that this raised to that power equals to this, right? That's what we've been working with. So that must mean, by definition, that b raised to the y power must be equal to x. Okay, remember, we're trying to solve for y. We want to know what y is. All right, so now what we can do is we can apply a log to both functions as long as it's the same log. And we can apply whatever log we want. So let's say we apply log base a to this side, b to the y, and we apply log base a to the other side. Right? We're maintaining that equality. We're applying the log to both sides, the same index, and a is anything you want, any real number, any real number, real number. Good. Okay, so now we have our properties of exponents. We can move this guy out in front and rewrite it as y times, and then we have log base a of b must be equal to log base a of x. And finally, we can divide both sides and say that y is equal to log base a of x divided by log base a of b. Good, good, good. Questions, 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 questions? Questions, questions, questions? Okay, so here is the exact same thing. We have that b to the y power, right? This comes from the statement that y equals to log base b, log base b of x. So b to the y power equals to x. Apply a log base a to both sides. Move the exponent out in front. And so we get this. Okay, how is this important? Okay, so for example, let's say that I wanted to find out what is log base 7 of 13. What in the world is that? I know conceptually it must mean that it's the answer to this thing. And you know, we use the variable x way too much, so I don't know if it helps for me to do a happy face. The answer is happy face, right? And what's special about happy face? Well, happy face is the number, it's a decimal number, so such that 7 to the power of that decimal, 7 to the power of happy face, must be equal to 13. Okay? All right, well, I can take logs to both sides, log base anything. So I can apply log base there, 7 there equals to log there. And here we have log happy face. Okay, so we can apply log base anything, log base 2 to both sides. That's fine. We can also apply log base 19 to both sides. Nothing special there. We could do that. But as long as I get to apply any log I want, why not pick a log that is easy to work with? So base 10, or just leaving it as log, is easy to work with because my calculator has a log base 10 button, right? Or the other popular one is log base e. So I can apply log base e to both sides, otherwise known as ln to both sides. And then it'll be an easy button on my calculator, right? So let me just leave it as log base 10, which means I don't put anything there at all, just log. And then I can move that exponent out in front, right? That's one of our properties of logs. So then this would be saying that that happy face would be times ln, oops, not ln, times log of 7 equals log of 13. And just so people don't forget, and we're still getting used to this, I'm just going to go ahead and write the 10. Log base 10, log base 10, log base 10. Okay, and now we divide both sides, and we get that this happy face, the answer that we were looking for, is equal to log base 10 of 13 divided by log base 10 of 7. Okay, we wouldn't want to have to do this work every single time. It's a very simple pattern that we notice. If we are asked to do a log of some index that is not a common one, not a 10 or not an e, then what we could do is change it to whatever base we want, something convenient like 10 or e, and then what we do is we create a division where the numerator is log of the index we were interested in divided by log of the base we didn't want to work with. Good? Maybe? Sort of? Common? No. Okay, so let's use our calculator to find this answer, just to confirm. So, launch calculator. So if we have log base 10, that's just going to be the log button. Let's get rid of this thing. Clear. Okay, so log of 10. Oops, not log of 10. Log of 13 is this. Remember, what is that decimal? This means that 10 raised to this decimal equals to 13. We can confirm it. 10 to the power of 1.1139, we'll stop there, is approximately 13. Pretty close, right? And then log of 7 is equal to this decimal. This must mean that 10 raised to the power of this decimal, 0.845098, approximately, would be pretty close to 7. Okay, so we have an answer to both of these two. Let's move it over here. And then we can scoot this guy over here for now. Okay, so from our calculator, we can see that this numerator is going to be the decimal 1.113939433352 divided by log base 10 of 7, which is this decimal, 0.845098, right? These two decimals. And now if I figure out what is the division of those two ugly decimals, let's just use our calculator over here. So then this is equal to 1.1139433352 divided by 0.845098. It gives us that decimal. So from our calculator work, we can get that this division of these two things is equal to 1.318123, approximately. Okay, let's step back and see what we just found. This might have confused some people. Okay, so we started with this up here. We wanted to know, what is this? What is log base 7 of 13? Conceptually, I should know that the answer to this happy face, the answer to this should be some decimal so that 7 to the power of that decimal equals to 13. And that's what this is saying. Good? So to confirm that it works out, it should be true that 7 to the power of 1.318123 should be pretty close to 13 if we did a good job. Right, so we can confirm it works. By saying that 7 raised to the power of 1.318123 1, 2, 3, approximately, should be pretty close to 13, and so it worked out. Good. Any questions about that? No, 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 no. Okay, so let's do one more example where we don't do all that work, right? So what this is saying is if we have the question is find, whoops, if the question is, find log base, I don't know, 13 of 52. 13 to what power equals to 52? That's what they're asking you to find out. You can go, well, I don't know. My calculator doesn't have an easy button for 13, log base 13. But luckily, thanks to this change of base function, we can change it around and say that log base 13 of 52 is the same thing as a division of, and then I can use any log I want. I don't want to work with 13. Let's say I want to work with ln of 52. But then you have to divide it by ln of the index here. The log that you didn't want to work with was 13, so you have to divide it by ln of 13. The division of these two will be equivalent to the answer to that one. Okay, so we go over to our calculator. I'm just going to do it on my calculator over here. So this would be ln of 52. This gives me 3.95, 3.9512 approximately, just to speed things up. And then ln of 13 gives me 2.5649. Right? And why is this true? This must be true because e raised to the power of this decimal equals 13. And e raised to the power of this decimal equals 52. So this is not the answer to our question. This is not the answer to our question, but the division of the two will be the answer to our question. So when we divide these two, approximately we get 3.9512 divided by 2.5649. We get approximately 1.5049 approximately. And so now that becomes our answer. Right? This is our answer to this. That's what we originally wanted to know. 1.54049. And we can check. Just getting check by noting that 13 to the power of 1.54049 is pretty close to 52. 13 to the power of 1.54049. Yep, pretty close to 52. Any questions? No? Okay, so here's our table indicating the change of base formula. Log base b of x equals to log base a of x divided by log base a of b, where the value of a is any real number that's positive, right? Logs have to have a positive index not equal to 1, or if it's equal to 1, it kind of becomes an obvious one. Good. Okay, so here's a couple really quick ones we can solve. Log base 8 of 5. Well, if I don't have an easy button to figure out index of 8 in my calculator, then I can say that this one, log base 8 of 5, let's use log base 10. Since that's a nice easy button on my calculator, is log base 10 of 5 divided by log base 10 of 8. Right, so those just become nice easy buttons on my calculator. So I can hit log of 5 equals to 0.69897 divided by, and then log of 8 So log base 10 of 8 is 0.90309 approximately. And then when I divide these two, I get 0.69897 divided by 0.90309. It's approximately 0.773976-ish, right? And we can check to see if it's true, if it all works out. It must be true that 8 to the power of 0.773976 is pretty close to a 5. Good. 7739, is that what the author got? 7739. Good. And they also use log base 10. We could just as easily have used log base e. Nothing special about log base 10. So just for the sake of making sure that works, we can have also said, let's try saying that this is equal to ln of 5 divided by ln of 8. Right? We can change it to any log we want, and ln of 5 equals to 1.6094 divided by ln of 8 equals to 2.07944. Remember, this is the decimal such that e raised to this decimal equals to 8. E raised to this decimal equals to 5. Notice that this right here does not match this, and this does not match that. However, this division will be equivalent to that division. The result of those two will be equivalent, approximately, right? Off by a little bit. And so we'll get the same answer. Any questions? No? 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 And so log base 9 of 20, let's just look the answer to that one. Log base 9 of 20 is ln of 20 divided by ln of 9. And we can just use our calculator, divide these two, and we get approximately this decimal. Try it on your own. And that must be true, right? If we check, it must be true that 9 to the power of 1.36342 is approximately 20. Any questions? No? No? Okay, this is a good place to stop. I think we finished section 4.4. Right, so we're done with section 4.4. We'll pick up on section 4.5. Please work on your homework and come back with questions tomorrow on anything. All right, have a great day.